us her results from kernel methods on the data integration challenge. Thank you so much.
Thank you. Thank you for the opportunity to present our work here. So just to recap from David's introduction for neuroblastoma, so it's the most extracranial solid childhood tumor, but it has high heterogeneity in prognosis. So some patients can have spontaneous regression, whereas others can develop rapid progression of tumors. And the most well-characterized molecular signature for neuroblastoma is MYCNX amplification. And the stage of the disease is also strongly associated with survival, where stage 4 patients have much poorer outcome compared to the other stages, and also age. So if a patient is diagnosed before 18 months, it has a much better outcome compared to the rest of the patients. However, if you stratify the patients based on these signatures or variables, you still have a very high variance in terms of survival. So that's why there were many other studies shown below. These studies correspond to gene lists where they came up with a much more detailed molecular profile to stratify the patients in a higher accuracy with a better distinct survival profiles. So here's the outline of my talk. First, I'll present supervised learning results in SEQC cohort. Then I'm going to show our results on using this model to predict this time outcome in some other cohorts. And lastly, I'm going to talk about our unsupervised learning efforts to learn subtypes de novo from this data. Okay, so first, this just single slide summarizes our results. So we use the linear SVM with 100 selected features from RNA-seq data. We found out that RNA-seq data works much better than microarray, and including microarray does not help. So feature selection was based on ANOVA p-values, and the cross-validation accuracy that we got for predicting OS was 0.83. You can compare this against 0.85, which was the best measured accuracy reported in the genome biology paper. And also on predicting EFS, our accuracy, we were able to get the best accuracy with this very simple model. And we also tried much more complicated methods such as boosting, random forests, and so on, but we weren't able to improve over this linear SVM model. And in the second part, so we asked this question whether this model can be used to predict clinical variables in other cohorts. And just to summarize again, we are using a linear SVM, this time without feature selection. And the C parameter in the linear SVM is chosen by cross-validation. And we use this option that sample weights are not uniform, but they are inversely proportional to class frequency to cope with this unbalanced data. And this time we are training this model on the whole SEQC data, not cross-validation, not training. And we are predicting, we are using 2 different cohorts. So this table shows the statistics. So the worst T cohort has 88 patients, and you can see the proportion of high-risk patients, number of deaths, EFS variables, and so on. And in the target cohort, we have 247 patients. And you see that this cohort is different than the other 2 cohorts because the proportion of high-risk patients is quite high. This is also reflected in OS and EFS proportions. And you can also see the platform to measure gene expression. So these number of genes in the here shows the number of common genes in SEQC data and these cohorts. So we first tried predicting OS, so the death, basically the death variable, inverse T cohort, and the area under the rho C curve is 0.98, meaning that we almost get perfect ranking, and the balance accuracy we got is 0.81. And we compared this to two other studies that predicted OS in the same data. So the first one, Totaro et al., uses only one gene, IL-6 gene, and this results in a balance accuracy of 0.65. And the other paper, Valentin et al., uses 157 genes with a better balance accuracy, but I should point out that this 150 genes were selected based on the microarray gene expression of this cohort versus T cohort, whereas our model was built entirely in a different cohort, which is the SEQC cohort. So that's kind of expected to get a better, to have a better performance. And this slide now shows the survival curves of these three models, and you can see that our prediction results in a better separation between the two groups, and this is also reflected in the p-value here. So we then moved on to predicting EFS. So this results in a slightly lower area under the rho C, and the balance accuracy is still 0.81. Then we moved to the target cohort, where our results got a lot worse. And we thought this is because of the proportion of high-risk patients in this cohort. It was quite large compared to the low-risk patients, and this was also reported in the original genome biology paper that predicting within the high-risk cohort is much more difficult. And EFS is similar with a better area under the rho C, but the same balance accuracy. And we also tried the strategy that what if we only train with the high-risk patients in the SEQC cohort and predict now only high-risk patients in the target cohort. Now the balance accuracy have increased from 0.51 to 59 if we do this. So that might be a good strategy for future studies to maybe only focus on high-risk patients if you want to predict high-risk patients. And in the last part of my talk, I'm going to talk about a method that we have used for unsupervised learning. So we have here different types of data, and we use this method called multivariate kernel k-means, where we use a kernel function. We use the RBF kernel, which is shown here, to transform from the input space to the kernel space. And what MVKKM does is it figures out the weights, so the contributions of these data types to the final clustering, and these clusters would correspond to subtypes. And here are some more details. I won't go over all the equations, but the idea is we can combine these three kernels. So KV stands for the kernel matrix for VV. V is just the data type, different data types. So we can calculate the composite kernel. In the beginning, we can initialize these weights with uniformly. And once we have the composite kernel, now we can run regular kernel k-means to do the clustering. And this is an iterative process where the next step now is to estimate these weights. There is a closed form solution for this. Here, dV stands for within cluster distance in terms of the data type V. So you can just use these equations to estimate the weights. And then you would go back to the calculation of the composite kernel and so on. So this is an iterative process. And after some time, it would, after some number of iterations, it would converge and you can get the weights. And to choose the number of clusters, we used silhouette coefficient. So it is calculated using this formula, where AI is the average distance to all the other samples within the same cluster, and BI is the average distance to all the samples in the closest cluster. So you would want AI to be much more smaller than BI. And in the end, you calculate this for all the samples separately, and you can take the mean to choose K. And when we apply this to the SEQC data cohort using all the patients. Now we are using only RNA-seq data here, so this is 498 patients. K was chosen to be 2, so we get 2 clusters. You can see that they are very well separated, which is also reflected in the p-value. And we also looked at the stage distributions. You see, as expected, stage 4 patients to be to have a higher proportion of high-risk patients. And we also ran multivariate Cox regression model to compare our clustering with the other known variables, age and stage. You see that our groups have a higher hazard ratio, which is 7.9. It has a much more significant p-value compared to the age and stage. That was pretty good. And in the next step, we only focused on those patients that have low MYCN expression, and we can still again recover two subtypes with good separation. Now this is a little bit worse than using all the patients, and again, these groups were still significant when we took into account age and stage in a multivariate Cox regression model. And lastly, we looked at a subset of patients. So these patients have ACGH data, and the MYCN expression is low. And when we used RNA-seq data only, we get this survival plot. But if we include ACGH data into the MVKKM model, the separation is much better, as you can see from the p-values. So including ACGH data in this case helped. And this is just to show you the weights that we learned. So we use actually 2 different versions of the same RNA-seq data. These are 2 different processed in 2 different ways. These are the weights, so they got equal weight, whereas the ACGH data got a little bit higher weight in this MVKKM model. And we also looked in this set of patients, 121 patients. We also looked into the genes that are differentially expressed between the 2 groups. And we see that some genes are downregulated, are expressed in lower amounts in the high-risk patient group, and vice versa. And the remaining genes show the exact opposite pattern. So we started to look into these genes. So one of them is the FOXO3, which is a transcription factor, and you can see many papers on this. So the fact that it is downregulated in high-risk patients agrees with the previous literature that its inactivation is seen in aggressive neuroblastoma. And MAP7 was previously reported in many papers. It was found to be associated with neuroblastoma, and many other genes are also relevant. So in conclusion, from the first part, we can reach the best performance with a simple linear SVM for the supervised learning part. In the second part, I've shown you that we can use this model trained on the CQC cohort to predict OS and EFS, so death and progression in other cohorts. And of course, the number of high-risk patients in that cohort affects the results a lot. And in the last part, I've shown you that this model, multi-view kernel k-means, can integrate data types efficiently, and it can discover subgroups with distinct survival profiles. And one last point is that, so right now we are only looking at this gene expression data and copy number data, but we've come across with many papers that also finds association of microRNAs with neuroblastoma. So in the future, if microRNA expression data becomes available for this set of patients or for some other cohorts, I think it would increase the accuracy of defining these subtypes. So I would like to thank my students, Ilyas and Tunde, who did the work on unsupervised learning. Alp did the cross-cohort prediction, and Saber helped with the data pre-processing. Thanks for listening.
Thank you for your talk. We can take questions, please. Okay.
I was wondering, you said in the beginning, right, with your linear SVM model, that RNA-seq works much better than microarray data. So do you have any idea why that is? Because usually in head-to-head comparisons that I've seen, they perform similarly and they basically measure the same thing. So do you know where this big discrepancy comes from?
Actually, there was no big difference. It was a slight improvement when we used the RNA-seq data. So I don't think there is like a big gap between the two data sets. But in this case, if you predict one patient, the label of one patient accurately, then those accuracies can change a lot. So I think there is no big difference.
Thanks.
Just following that, because RNA-seq can give you really more information. I mean, it was just analyzed on gene level or transcript level?
It was gene level.
And why?
Why didn't we analyze the transcript level? Because when we're doing this cross prediction with the other cohorts, those cohorts had only microarray expression data, so we were going to use, we needed gene expression there. We will have to combine the transcripts to gene expression anyways to do that. So that's why in the beginning we just used gene expression data.
Okay.
Okay, are there any more questions? May I perhaps follow up on this question about the difference between the platforms? There have been some reports, for instance, from Wei-Tong's laboratory, that by direction of trying to transfer conclusions across platforms, say from RNA-seq to microarray or from microarray to RNA-seq, can make a difference in performance. Did you look at all into learning from one cohort and applying to the other, and then trying it the other way around, learning on the second cohort and applying to the first one? Did you look into whether that had any effect on the observations that you had?
We haven't looked into that. So like training from the worst cohort and predicting on. No, we haven't checked that. But we checked using the microarray data on SEQC to predict again Versteeg, and it resulted in somehow lower accuracy. So that was interesting. So RNA-seq somehow again had better, I don't know, I can't remember the difference, but it worked much better.
Okay, so you actually had three platforms, right? You had the adjuvant in the seq-C and the RNA-seq, and then you had the Affymetrix and the other cohorts that you looked at.
That's right, that's right.
Well, thank you very much. We come to the last speaker of this morning's session.